Hi there, this is section 6.2 and 6.3 continued. We are going to now look at something called the law of exponential change. And you guys have studied exponential growth and decay functions in the past, which you guys know from your experience with exponential growth and decay functions that exponential situations that can be modeled by exponential growth means that the more you have, the more you get. And for exponential decay, the less you have, the less you lose. And those quantities are growing or decreasing by a factor or percentage at regular intervals or over a period. If I taught you exponential growth or decay, I always refer to it as a quantity that is growing or decreasing by a common percentage per period. And this can be stated equivalently as the rate of change of a quantity is directly proportional to the quantity itself. Mathematically, that means that dy over dt, which is the rate of change of y with respect to t, which is probably time, right? We usually talk about growth or decay as being a function of time, is equal to some constant k, where if k is positive, it means that growth is happening. If k is negative, it means decay is happening, times the function itself, the exponential growth or decay function itself, which is y. So we can find the general solution to this equation using the method that we've been using in these two sections because it's a separable differential equation. So getting y and dy on one side, and we're going to have k and dt on the other. And remember, k is just a constant. So when we integrate each side of the equation here, oh no, sorry. That would be 1 over y because we're thinking about dividing by y. So we integrate 1 over y, that ends up being natural log of absolute value of y equals kt plus c because we're integrating with respect to t. Okay, we've done problems like this, so rewriting in exponential form, we're thinking e to the, where did c go? E to the kt plus c power is equal to absolute value of y. And then rewriting the right-hand side as we'll have absolute value of y is equal to e to the c times e to the kt power. E to the c is just a constant, and then if we rewrite as y equals to plus or minus e to the c times e to the kt, plus or minus e to the c is still an arbitrary constant. So we can just replace that with c. You'll see some text, again, refer to when you initially integrate that plus c, they'll say it's plus c sub 1 or use a different variable before they just rewrite this part as c. So y equals c times e to the kt. Okay, that's the general solution to dy over dt equals to k times y. Okay, so if that is true, then y is equal to c times e to the kt power, where blank is the initial amount present. Well, initial amount usually means when no time has passed, like the amount that you're starting with. So like when t is equal to 0, well, if t is equal to 0, right, e to the 0th power is just 1. So c would represent the initial amount present, which also corresponds graphically to the y-intercept of the graph. Okay, so let's work through a few of these exponential growth and decay problems. So the population of bacteria in a culture increased from 400 to 1600 in 3 hours. Assuming that the bacteria population P grows according to the rate equation dP over dt equals to K times P, where T is time in hours, find the value of K. Okay, well, we don't know what the initial time is, but we are given two different populations where we can think of 400 as being our initial population, T equals to 0, and then 1600, that population would correspond to T equals to 3 hours. Okay, so then we know that the solution to this would be P equals to C times e to the kt power. You could double check that if you want, but that's what we'd get based on what we did above. So in this case, C we're going to replace with 400, and then we can plug in 3 for T and 1600 for the population. So that K is the only remaining unknown. And then we can solve. So if we divide 1600 by 400, we would get 4 equals to e to the 3k power. And then rewriting that in log form, which you can also think about taking the natural log of each side of the equation, you would end up with ln of 4 is equal to 3k. So that means, flipping this around, k is equal to natural log of 4 over 3. Okay, and then next, how fast is the population of bacteria increasing when the population is 3,000? Well, since we now know what k is, we can use our dP over dt formula. So dP over dt evaluated when t is equal, when p is equal to 3,000. That's going to be k is natural log of 4 divided by 3 and then times 3,000. And the units will be bacteria per hour. And you could simplify that more. What that ends up being 1,000 times natural log of 4. You could unplug it, and you could write that as ln of 4 to the 1,000th power bacteria per hour. Okay, next question. So the weight of a population of bacteria is given by the differentiable function B, where B of T is measured in tons and T is measured in hours. The weight of the bacteria population increases according to the equation dB over dt equals to K times B, where K is constant. At T equals to 0, the weight of the bacteria population is 3 tons and is increasing at a rate of 2/5 tons per hour. What is an expression for B of T? Well, we know that B of T will end up being in the form C times e to the kt power. But we need to figure out what K would be, and we also need to figure out what C would be. Well, we know what C is, because when T is equal to 0, the population is 3 tons. So we know that B of T is equal to 3 times e to the something times T power. Okay, and we can solve for what K is based on the fact that when T is equal to 0 and is this rate, so when B is equal to 3 tons, it's increasing, the weight is increasing at a rate of 2/5 tons per hour. So we can actually go back to a rate of change equation here, and we can solve for K. So we can replace dB over dt with 2/5. And then at that same time, the population is 3 tons. So that means that K, and make sure you're paying attention to units and making sure that they all match up and you're not having to convert everything. The weight's in tons here, so that's fine. And then if we multiply by 1/3 on each side, that would be 2/15 for K. So to finish answering the question, B of T would be equal to 3 times E to the 2/5 T power, where B of T is measured in tons and T is in hours. There we go. Okay, 2012 AP exam free response question. Okay, the rate, let's see, what color do we want to use? Let's use like burnt orange. There we go. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals to 0, when the bird is first weighed, its weight is 20 grams. If B of T is the weight of the bird in grams at time t days after it's first weighed, then dB over dt is equal to 1/5 times the quantity 100 minus B. Notice if you were to distribute that 1/5, what you would have. Okay, so let y equals to b of t be the solution to the differential equation above with the initial condition b of 0 equals to 20. Okay, question A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. Okay, well, this is just using the given equation, dB over dt, and plugging each of those weights in for B to see which rate is larger. And it says when the bird is gaining weight, so that better be a positive rate as well. So dB over dt, this is for A. When B is 40, ends up being 1/5 times 100 minus 40, which is 12 grams per day. And then dB over dt, when B is 70, is 1/5 times 100 minus 70, ends up being 6 grams per day. Okay, so we can say the bird is gaining weight faster when it weighs 40 grams because 12 grams per day, or you could say dB over dt evaluated at B equals to 40 is greater than 6 grams per day. Or you could represent the 6 grams per day as dB over dt, evaluated at B equals to 70. Okay, question B. Find d squared, oh, sorry. Sorry, I'm tired. That's the second derivative. Let's find the second derivative of B in terms of B. And then we're going to use the second derivative to explain why the graph of B cannot resemble the following graph. Well, I have a feeling that we are going to be examining the concavity of B since we're dealing with the second derivative. So let's first of all go ahead and define the second derivative. Now we could think about having the 1/5 pulled out, and then derivative of 100 would be 0, and then minus the derivative of B with respect to t. So the second derivative would be negative 1/5 dB over dt. But it says to find the second derivative in terms of B. Well, we know what dB over dt is, right? We could replace dB over dt. So we can say that this is equal to negative 1/5 times 1/5 times the quantity 100 minus B, which is negative 1 over 25 times 100 minus B. Now, if we find the possible second derivative, right, tells us about concavity, we could find possible point of inflection by thinking about setting the second derivative equal to 0. So we can see when B is equal to 100, that's a possible point of inflection. And then looking at an analysis line, which this part, remember, is not graded. We have to explain the results of our analysis line. Now, if we were to substitute in a value between 0 and 100, we'd get a negative value, because that would be the negative 1 over 25 times a positive value, which would be negative. So on that interval, the graph should be concave down, looks like a frown. Is that the case? No, it looks like for B between 20 and 100, that there's actually an interval where the graph is concave up, not concave down. So that's going to be, and then to the right of 100, so for greater than 100 would be concave up, because the second derivative would be positive. Okay, so for our explanation, we could say the graph of B must be concave down on the interval from 0 to 100. Because the second derivative is less than 0 on this interval. However, the given graph is concave up. on part of this interval. Therefore, this graph cannot represent B. Or something like that. Okay, part C. Notice this says use separation of variables. It's literally telling us the method to use in order to find y equals to b of t. The particular solution to the differential equation with the initial condition b of 0 equals to 20. It's telling us the method. So we just need to take our differential equation and solve it. Hey, there we go. Okay, so I'm going to divide by the quantity 100 minus b on each side of the equation here. And then I'll have 1/5 and multiplying by dt on each side of the equation. This sets me up for where I can integrate. I need to do a u sub on the left-hand side. So du over db is equal to -1. So we can say negative du equals to db. So rewriting the integral as -1 times the integral of 1 over u db. And then the right-hand side will just be 1/5 t plus c. Make sure your t's and your pluses look different. And then integrating the left-hand side, that'll be negative ln of absolute value of u. And then substituting 100 minus b back in. Okay. And we're solving for a particular solution. So I'm going to substitute 20 in for b and 0 in for t. Okay, so c ends up being negative natural log of 80. So we have negative natural log of absolute value of 100 minus b equals to 1/5 t and then minus ln of 80. And we need to get to the form of y equals, or b of t equals. So we need to isolate b. We're trying to get to b. So I'm going to multiply by -1 on each side. So that'll be ln of 80 minus 1/5 t. And now rewriting in exponential form, right? E to this power is equal to the absolute value of 100 minus b. Okay. And then we can think of the right-hand side as e to the natural log of 80 plus -1/5 times t. And then rewrite this. I think that would be nicer than e to the natural log of 80 divided by e to the 1/5 t. I would rather have I don't want t in the denominator. So this can be written as, oh, here, let's do this in 2 steps. So e to the ln of 80 times e to the negative 1/5 t. And then notice, this is just 80. Okay, so then just a couple more algebra steps. So if we were to subtract by 100 and then divide by -1, we end up with b, which I'm going to write as b of t. So that's what they were asking for. B of t equals to 100 minus 80 times e to the negative 1/5 t. So that is our particular solution. This is for t greater than or equal to 0. Yeah, that's our, yes. So here is the particular solution. And I stated the t greater than or equal to 0 because otherwise this has a domain of all real numbers. It's just an exponential function. But for this situation, since t represents time, I'm explicitly stating that t has to be greater than or equal to 0 for this function.